This is a video that covers section 6.7, part 2. And we're going to start on page 3. So I guess this will be your slide number 6. The title is Projection of a Vector onto Another Vector. And we have a little picture here to kind of like explain what we are going to do. And from the last video, we discussed the fact of, I'll just go back so you can see it. And so we called that two vectors are parallel when the angle between them is either 0, that happens when two vectors go in the same direction, the angle between them is 0, or when they go in opposite directions like here, the angle between them is 180. So that's what we call vectors when vectors are parallel. Also, we use the word orthogonal to denote two vectors that are perpendicular to each other, like these two vectors here and here. And so the fact that a vector is orthogonal to another vector is actually kind of important in physics and in linear algebra. So the explanation for that is that, and we're going to use the notation that you guys see here. And the way we read it is the projection of V onto W. So what we're going to do is we start by considering two vectors, and one of them is vector V. It's right here. And we also have vector W. Actually, I'm going to use this other example. Okay, so I had to pause the video because I had to think a little bit, and I was thinking that this was the same example, but there are actually two examples. So let's do one at a time. So for the first case, this will be vector V, and so this one is vector W. And so you guys can see clearly that the vector between those two angles is not 90 degrees, correct? So we could say that vectors V and W are not orthogonal. So now the projection of vector V, which is this one, onto W, that means that we want to make a vector that will be perpendicular with the other. And so that one is going to become this long vector here. And so what we see now is that that projection is actually perpendicular with the other vector, with vector V. So now let's look at the other example, and we start with vector V, it's here. And then vector W is going in this direction. And so you can see very clearly the angle here between them is an obtuse angle. It's more than 90. So we could say that the two vectors are not perpendicular. However, after we do some computations, we could create another vector, and that will be this one here, and that's the vector, the projection of vector V onto W. And so for that vector, we could see here that that one, it is orthogonal with vector V. And also, another thing to consider is that what happens with the projection and with vector W is that those end up being parallel. In this case, there's 180 degrees, and in this case, there's 0 degrees because they're both going in the same direction. All right. So let's go and see a little short proof of what the projection is. And so for that, we're going to use the image that we have here. I'm just going to erase a little bit of it. Okay, and so we're going to find what the cosine is. And of course, we all know that cosine, it is defined as the adjacent, cosine of theta is defined as the adjacent side to theta divided by the hypotenuse. Okay, and So what we're going to use is the formula that we have here. And so we are considering this right triangle that you can see here. Here's the right triangle, and here's the angle theta. And so we know that the adjacent side to theta is this one, projection of V onto W. And so for that one, since we want the length of that vector, we're using magnitude. So that's why you see the symbol there. That will replace the adjacent side. Now for the hypotenuse, you can see very clearly that one is the one opposite to the 90-degree angle, so that one happens to be vector V. But again, we want the length of it, so we use magnitude of vector V. That's why we have that symbol. Okay, so going back to this formula, what we're going to do now is we're going to move or multiply by the magnitude of V, or in other words, move the magnitude of V to the other side. Since it is dividing, once I move it across, it's going to be multiplying. So it will be the magnitude of vector V times the cosine of theta is equal to the magnitude of the projection of vector V onto W. Okay, now from here, what I'm going to do is just reverse the equation. So I just want to have the magnitude of the projection of vector V onto W on the left side. And then on my right side, I want to have the magnitude of V times the cosine of theta. Okay. And so now what I'm going to do is I'm going to use the other side, and then in a minute we're going to come back to this side here, okay? So what I want to do is, I don't know if you remember the alternate form for dot product. So we had an easy one where we would just multiply a sub 1 times a sub 2 and then add it to b sub 1 times b sub 2. That was a way to find the dot product. Now the one that I'm talking about, the alternate form, that one goes like this. So the dot product between v and w is equal to the magnitude of v times the magnitude of w times the cosine of theta. And so that's what I want to use right now. So I'm going to erase the easy formula so that we don't get confused. We're only using the alternate form. Okay, and so what I want to do now is I'm going to take the magnitude of w, and since it is multiplying to the magnitude of v and to the magnitude and to the cosine of theta, I want to move it across, and so you all know what's going to happen. So we need to divide. So we will have the dot product of v dotted with w divided by the magnitude of w is equal to the magnitude of v times the cosine of theta. And so the reason I did this is because what we left off here was the same thing, right? Magnitude of v times cosine of theta. And so that's what we have here. So now what I'm going to use is I'm going to replace the statement here with what I got here. Okay, so that will be v times, sorry, not times, but dotted with w, divided by the magnitude of w is equal to the magnitude of the projection of vector v onto w. Okay, and so that is the formula we're going to use. Now, that is only going to give us the magnitude. Now, how can we find the vector? Remember, magnitude is going to equal to a number. It's just a constant. But if we want the vector in terms of I and j, we have to do something else to it. And so to find that, the vector, what we're going to do is multiply this part, which is the magnitude, sorry, not the magnitude, but the dot product divided by the magnitude, and we're going to multiply it by something called the unit vector. And so the unit vector, I'll refresh your mind a little bit. We discussed that there, not there. Oh. You can't find it. Okay, it's not there. Okay, this is a little weird. Maybe the unit vector was in section 6. Okay, so yeah, the unit vector was in section 6. So 6.6. But just to remind you what the unit vector was, it was a vector whose magnitude was equal to 1. And so the way we were finding those vectors was by taking the vector itself and dividing it by its own magnitude. And I should use W instead. Okay, and so the reason we do this is, remember, this was the formula to find the magnitude of the projection. This is the magnitude. And this is the actual vector, the one that will be given in terms of I and j. Okay? So we do this, we have to multiply by the unit vector. And so if we do that, we're going to end up with a formula that looks like what I'm going to write down. So it will be the dot product of V dotted with W divided by, and what I'm going to do here is I'm going to take these two magnitudes, and if I take them and multiply them, then I will have that same magnitude but squared. And then you might be wondering, there's still a W there, and that W is going to be here. And I'll show you what we will do with that formula in a minute. So to find the vector, this will be the formula. And remember, the way we call it is the projection of V onto W. Okay, so let's go ahead and answer the first problem related to this. And so we have the formula here. You do not need to memorize it. I will have that formula on the test. But for all of those, all of you who would like to become an engineer, I will suggest that you try to memorize it because it will come in very handy. So we have here two vectors, and as you can tell from the picture, we have the first vector, which is vector B, and those are the coordinates 2i plus 4j. So we have the vector here, initial point is at the origin, and the terminal point has the coordinates 2, 4. Also, we have vector W, and that one is here. And that one has the initial point at the origin as well, and the terminal point has the coordinates -2, 6. Okay, now we can tell that those two vectors are not orthogonal because the angle between them is not a 90-degree angle. So now to find the projection vector, which is going to become this one here, You could see it graphically. That will be the projection of V onto W. That one is, it has the same magnitude as W, but it is perpendicular to vector V. Okay, so let's go ahead and follow the formula. So even though we have it there, I'm still going to write it down. And so we need the dot product between V and W. I'm going to divide by the magnitude of W squared, and then we're going to multiply by the vector W. Okay, so we're going to do everything one step at a time. And so to start, I'm going to make my substitutions. And so remember the dot product, it is pretty simple, but I'm still going to write down the vectors. So vector, the first vector is vector B, so that one has 2i plus 4j. And vector W is negative 2i plus 6j. And don't forget we have here vector W. So I'm just going to make note of that here. And on the bottom, remember the magnitude is the square root. We use Pythagorean theorem, so we're talking about this one. So we will need negative 2 squared plus 6 squared. And don't forget, we're squaring the magnitude, so we need a square here. And that's actually very convenient because the square is going to cancel the square root. And let's take care of the dot product on top. And remember the dot product, you take the horizontal components and you multiply them. So we will have positive 2 times negative 2. And then add the product of the vertical components. So 4 times 6. That is the dot product. Now here, we're going to have the square root and being squared, that cancels out. And so now we have only what's inside the radical. So negative 2 squared is equal to 4, and 6 squared is equal to 36. Now, let's not forget that we still need to multiply by vector W. Okay, so 2 times negative 2 is negative 4, plus 4 times 6 is 24. On the bottom, we're going to have 40. We're still multiplying by W. And so this will be negative 4 plus 24 is positive 20 divided by 40. We're still multiplying by vector W. And so here, 20 divided by 40 is equal to 1/2. And now, vector W, what I'm going to do is take the whole vector. So that will be negative 2i plus 6j. And now I'm going to go ahead and multiply by that number that we found, which is 1/2. So 1/2 times negative 2 is equal to negative 1. Just write it down. So negative 2 divided by 2i. And then if we multiply 1/2 times 6, that will give me 6/2 times j. And of course, if we simplify, we will end up negative 2 divided by positive 2 is negative 1. So we will have negative I. And then 6 divided by 2 is positive 3, so we will have plus 3j. Okay, so the checkpoint 4, I'm going to leave that problem for you to work on. And just in case you are curious, the answer for that one is equal to 7/2 times I plus, not plus, minus 7/2 of j. And that will be the answer for the question, what is the vector that represents the projection of V onto W? Okay, I want to make a correction. Earlier, I said that the vector here was the same magnitude as W, and that is obviously a mistake. You can see very clearly that W is way longer than the projection vector. So what I should have said is that this vector, the red one, the projection of V onto W, is the same magnitude as vector V, and it makes a 90-degree angle with itself, not with itself, but with vector V. So same magnitude as V. All right, so let's go to the next slide for the next problem. And so that one is, it talks about how to decompose two vectors. And so to decompose two vectors, we're going to let two vectors, V and W, be two non-zero vectors. And the first one, vector V, we're going to express it as the sum, so the addition of two vectors that happen to be orthogonal. And those two vectors, we're going to call them V1 and V2. And so if vectors V1 and V2 are orthogonal, that means that the angle between them is 90 degrees. Don't forget that. So also, what we know is that vector V1, V sub 1 is parallel to W, and also that V sub 2 is orthogonal to W. Okay, so what we're going to do is use the formulas that are given to us. So since we know that vector V sub 1. Okay, so I was able to graph the vectors, and then by using the vectors of the example, and provided that I already know the answer for this problem, I was able to graph everything. So I was able to graph vector V, vector W, vectors V sub 1 and V sub 2. And so with that image, I'm going to explain to you what it is said here. Okay, so we're going to take it slow. We're going to go step by step. And so what I want you to do is just to keep your paper handy and look at what I'm going to be showing you as I graph the vectors using the software GeoGebra. So what I'm going to do is read the statement. Let the two vectors be two non-zero vectors, and I'm going to be showing you with the graph as that will be appearing as I'm reading the statement. So we start with the vector V can be expressed as the sum of two vectors, two orthogonal vectors, V sub 1 and V sub 2. So let me show you what I came up with. So we start here. And so let's go back to the beginning, and we say that vector V could be expressed as the sum of two vectors, V sub 1 and V sub 2. And so let me show you that. So V sub 1 V sub 1 and V sub 2. If we add those two vectors, remember I was not able to show you how to do that, but let me see if I can do it here. If you add those two vectors, the resultant vector will be vector V. So it's that one there. And let me see if I can do what I was trying to do last time. No, it's not going to work. So let's just leave it there. Oh no, I messed up. So that vector was supposed to be at 3, 1. Great. So that was really bad idea. Okay, there it is, at 3, 1. Okay, so what I was trying to show you was how I was going to try to move this vector from here and position it here so that you could see how just by kind of like carrying it from here to here, it gives us a representation of what we talked yesterday, that you position the resultant vector, this one here, you get it by positioning the terminal point of this vector with the initial point of the other vector. But I don't want to get you confused with that, so let's just delete all that. So anyways, with this, it proves that if you add vector v sub 2 plus v sub 1, you get vector v, which is what I'm saying here. Okay, now our paper also states that vectors v sub 1 and v sub 2 are orthogonal. And that one is stated right here. V sub 1 and V sub 2 are orthogonal. And if you remember, that means that there should be a 90-degree angle in between those two. So those two are perpendicular. And so here's my 90-degree angle to prove it. So we could say that V sub 1 and V sub 2 are orthogonal. Okay. Also, the statement says that V sub 1 is parallel to W. So let me show you how those two look. So V sub 1 and W are parallel. And you can see that because for two vectors to be parallel, the angle in this case, since they're going in the same direction, the angle between them is 0. So yes, those two are parallel. So we say that V sub 1 and W are parallel. Also, the statement says that V sub 2 is orthogonal to W. So let's see if that is true. So we have W and V sub 2, and for them to be orthogonal, the angle between them should be 90 degrees. And we could see clearly here that, not that one, sorry. They are 90, the angle between them is 90 degrees. So yes, we would say that V sub 2 and W are orthogonal. Okay, and so what we know here is that something interesting, that V sub 2 is actually orthogonal to W, and it's also orthogonal to V sub 1. Okay, so that was just to explain to you guys what was on top of the statement. Now going back to this one, so everything that I explained graphically is what it's saying here, okay? And we'll post the video and we'll upload it to Edmodo, and if you want to see this again or pause it or play it in slow motion, you're free to do so. Okay, so now what I'm going to try to do is explain to you guys what are we going to do with this formula, and I'm going to try to see if I can do that graphically. So what we're going to do is we're going to kind of force this vector V sub 1 to be a projection of vector V onto W. So what we're going to do graphically, let me show you that. So we start with two vectors, vector W and vector V. And so we want vector sub 1. Now remember that I already solved the problem and I know what the coordinates are. But at this point, you guys don't know that. And so at this point, we're going to start solving this problem, example 5. And so as you can see, the two vectors that are graphed there are the ones representing this. So let's look at vector V. And that one has the initial point at 0, 0, and the terminal point is here at 2, 4. Now for vector W, and that is because for vector V, we're giving the horizontal component 2, so 2i plus 4j. And now for vector W, we are given the components negative 2i plus 6j. Okay, so vector W has the initial point here at the origin at 0, 0, and the terminal point is here at negative 2, comma 6. Okay, so we start with those two vectors, and so what I'm going to do is create v sub 1 so that it is orthogonal, not orthogonal, I'm sorry, so that it forms a 90-degree angle with vector v. And so to that, I'm going to draw the segment to demonstrate that. And so that will be the segment connecting them, and yes, then the angle that we have here is 90. And I want to make a correction again. Earlier, I said that these two vectors, well, first of all, I made a huge mistake of saying that this vector and this vector will have the same magnitude, which is obviously wrong. Then I corrected myself and I said that this vector and this vector will have the same magnitude. Now, as I was going through the graphing process, I realized that that was a huge mistake. And this is a right triangle, so of course this side is not the same, does not have the same length as this one. This one is longer, so I'm going to correct myself again and tell you that this one, which will be the projection, v sub 1 is actually the projection of vector v onto w, is not, does not have the same magnitude as vector v. Okay, so just so you know. All right, so that's what we're going to do. That's the first part of the problem. So let's go ahead and work it out so you know how I was able to get those numbers. Okay, and so I'm going to start with this side. And remember that we're trying to decompose, and all we know is that vector v is the same as the sum of vector v sub 1 plus v sub 2. Okay, now v sub 2, all we know is that it is orthogonal to w, and we also know that v sub 1 is parallel to w. So what I'm going to do is force v sub 1, not force it, but make it be the projection of vector v onto w. So that was the little image that I show you here. That's what we're trying to get, this vector here. So numerically, what we're going to do, or algebraically, we're going to use the formula given to us to find that, the vector in terms of ij. So the formula states get the dot product of v dotted with w divided by the magnitude of w squared, and then multiply times the vector in terms of I and j. So this will be 2 times negative 2 plus 4 times 6 divided by the square root square of negative 2 squared plus 6 squared. And let's not forget we have to multiply by w. Okay, so we're going to get negative 4 plus 24 and divided by, remember the square root cancels with the square, and on the bottom we have 4 plus 36. We're still multiplying by w. And so this will equal to 20 divided by 40 times w. And so we know 20 divided by 40 is 1/2. And w, for w, I'm going to look at the top of the problem and get the coordinates for it. And we see here it's negative 2i plus 6j. So negative 2i plus 6j. So v sub 1 will equal to 1/2 times that will equal to negative. So negative I, and then 1/2 times 6j will equal to positive 3j. Okay, so now that we have that vector, we're going to use that. And going back to the image here, this is what we found algebraically, this vector here. And it is forming a 90-degree angle with vector v. And it is following the same direction as vector w. So that's why we say the projection of vector v onto w, because it is right on top, overlapping with it. So now that we know vector v sub 1, we're going to go back here. And we're going to decompose, we're going to use the statement that we have here. And now that we do know what the vector v sub 1 is, and we know what the vector v is, so we know this two. The only one that we don't know is v sub 2. So to solve for it, what I can do is, I'm going to leave my v sub 2 there, and then on the left side I have vector v, and then I take vector v sub 1, so that will be minus v sub 1. And so that is what I'm going to do. Now, if you recall from the problem, we have the coordinates for this vector, vector v. And so those are 2i plus 4j. And after all the stuff that we did here, we were able to find the coordinates for vector v sub 1. And so those are located right here. And so that will be negative I plus 3j. And so that is going to give me vector v sub 2. So here we're subtracting two vectors. So we have 2i, I'm going to clear the parentheses, 2i plus 4j. Negative times a negative is a positive. And then negative times a positive is a negative. Now we're going to combine like terms. So the horizontal components, 2i plus I is 3i. And the vertical components, 4j minus 3j is positive j. And that is equal to v sub 2. Okay, so now you might be thinking, so what are we even talking about? What are we solving for? And so let's go back and look at the question. And so the question was to decompose. The question is here. Decompose, or the instructions, decompose vector v into two vectors, v sub 1 and v sub 2. And so that's what we have accomplished. I know it feels like nothing, but that's how math is sometimes. So what we did was we took vector v, and we found what those two vectors were. And if you notice, we started from nothing. All we had was vector v and vector w. The first thing we did to find vector sub 1, we did all this process that is here, and then this is what we found. So we found that that one was negative I plus 3j. After that, by using the equation that we have here, this one, since we already know what vector the I and j components of vector v, and we knew that I and j components of vector v sub 1, we solve for v sub 2 to find the I and j components of it, and that's what we found here. So this part right here, that is v sub 2. And so if we add them, and this is just like to check your answer. If we add them, we will get 3i minus I, we get 2i. And 3j plus j, we get 4j. So remember, this is just to check our answer. And so we could verify that we did everything correctly because that was the answer for B, 2I and 4J. Now let me show you one more time graphically what we did. Okay. And so we started with those two vectors, and we knew that this vector was given by the addition of two vectors. So we were able to use the projection formula to find v sub 1, and that one is here. And we can see that that one forms a 90-degree angle with, not that one, sorry, with vector v. So it is the projection of vector v onto W. So we did that, and then by doing the algebraic manipulations, we were able to find v sub 2, which is here. And just so you know, again, that it is if you add v sub 2 and v sub 1, you get vector v. So for that, I'll show you here. And you can see that if you add those two vectors, this is called the parallelogram rule, and so this is the resultant vector of adding those. But remember, what we did was decompose. So instead of adding this plus this, we did not exactly subtraction, but we had to do some vector operations to find those two vectors. Okay? All right. So the good news is that the next problem is a lot easier than that. So I'm sure you will appreciate that. And we're almost done with this video. So just stay with me. Okay, so now this problem, you guys have done it in physics probably, and it is an application of the dot product. And for this one, we're going to be using the alternate formula for the dot product. And just to remind you what that formula was, it was the dot product of V dot of W, it is the magnitude of V times the magnitude of W times the cosine of theta. And so we're going to do something similar here. This is a W, just in case you wondered. And so we're going to do something similar here, but what we're going to use is this formula. So we're going to use W for work, and F is the force that it is moving the object from point A to point B. So what we have here for force, we're going to be using the magnitude of that force. And here the F is bolded, so it's representing the vector. And then in this case right here, it is not bolded, but it does have the magnitude symbol. And then the one that we see here is the magnitude of the force that is moving in this case, the sled from point A to point B. And so let's see. So I'm going to read the problem. So the problem says a child pulls a sled along level ground by exerting a force of 30 pounds. So this right here, it is the magnitude of F. 30 pounds. And now the 200 feet that we see here, well, let me go back a little bit. So he's exerting a force of 30 pounds on a rope that makes, and this is that vector in question, the 30 pounds, and that makes an angle of 35 degrees with the horizontal. And so that angle of 35 degrees, this is the horizontal, parallel to the ground, and it makes a 35-degree angle here. You can see it here. Okay? And so that is going to be the angle between the two quantities that we're going to multiply, between the two vectors. So how much work is done by pulling the sled 200 feet? So now that 200 feet is going to take place of this one here. So the length of the distance from point A to point B. Okay, and then of course we know that the angle between them is 35 degrees. Okay, so to solve this problem, it's pretty simple. We'll use the formula. So the magnitude of F multiplied by the magnitude of AB times the cosine of theta. And so let's substitute the quantities that we know. So the first one is 30. The next one is going to be 200. And here we have cosine of 35 degrees. And so you can enter everything on the calculator at once. Make sure your calculator is in degrees. And so what we get here is 4,915. And the units, because we don't want to upset Mr. Vaca, since here we were talking about pounds, and here we were talking about feet, the units are just going to be called pound feet. Maybe there's a better word for that, but that was the one that the book was giving. Oh, sorry, the book says foot pounds, or I don't know if there's another special name for it. Okay, so I'm going to leave the last problem for you to work on your own, so you can do that until the end of class. And make sure you do have a good weekend and do your homework. If you need an extension or something, just contact me through Edmodo. Goodbye.